Hello everyone and welcome to our webinar on EMI concepts and board shield design guidelines. My name is Lee Branham. I'm an applications engineer at LeaderTech and I'm going to be guiding you through our discussion today. So to start with a little background on our company, LeaderTech is located in Tampa, Florida. We've been in operation since 1984. We'd like to think of ourselves as a full-service EMI solutions manufacturer. We specialize in circuit board, enclosure, cable shielding solutions, and we also offer a full line of thermal products. You can see here that we really work with all aspects of industry, aerospace, military, commercial, and at this time we have 130 employees, and we do all of our manufacturing in-house at the Tampa facility. So LeaderTech is a subsidiary of HEICO Corporation. HEICO is located in Hollywood, Florida, and what HEICO does is they are the largest provider of non-OEM replacement parts for the airline industry. They operate in two segments. They have a flight support group, and then they also have a electronic technologies group, which is what we're a part of. You can see they're a $2 billion plus company, and they acquired us in 1999. So the advantage of being owned by a larger parent corporation like this is that they're able to give us the capital support that we need to better support our customers. In this webinar, we're going to discuss the concept of EMI, as well as the guidelines for designing effective board level shields. So what is EMI? EMI stands for electromagnetic interference and is essentially signals emitted either from or received by a device that disrupt its performance, similar to like a cell phone that could interfere with a speaker or TV. You don't generally see that happen in your day-to-day because those devices are shielded. Um, if you look at the chart of the electromagnetic spectrum, we're looking at primarily the radio and microwave zone, uh, just below the spectrum of infrared and visible light. The goal of EMI shielding is to mitigate this interference by creating a Faraday cage around the affected component. The total reduction in the signal is a combination of reflection loss within the Faraday cage and absorption loss actually within the material of the shield or cage itself. So what would be an example of a perfect shield? The ideal shield is a large, thick, hollow sphere of iron with gold plating for maximum conductivity and no seams, gaps, or openings. Um, Obviously, this isn't manufacturable or feasible because you wouldn't have any openings for power cords, cables, connections, anything like that. So we have to design our shields so that they still work in the real world, but they still provide the best levels of shielding effectiveness. In this slide, I've got a couple of basic shields. They're just one-piece boxes, as simple as it gets. And what I'm trying to show here is designing for apertures. When we talk about EMI shielding, we're trying to reduce the linear aperture. So if you look at the frequency wavelength chart in the center here, let's look at 5 gigahertz frequency and go over to the right to the 1/20th wavelength column. So you can see the maximum allowable opening is 3 millimeters. So for the shield on the left, we've got just a standard corner. So with the standard corner, it's cheap and easy to manufacture, but you're limited by the height of the shield. So if you had a 5 gigahertz frequency in this shield, the maximum that wall could be would be 3 millimeters. Otherwise, you're going to release signal and reduce your shielding effectiveness. So one design that we like to use is the interlocking corner. So you can see the shield on the right here. We've got an interlocking corner. So they're almost like teeth. So we when you form the walls of the shield down, the teeth interlock and break up that linear aperture. So rather than having one long seam like you do over here, you have several smaller openings to give you better shielding effectiveness. Here I'm going to show you a few examples of different types of shielding products. You can see here on the circuit board, this is just a basic rectangular shield frame. It's part of a two-piece. This frame gets soldered onto the circuit board, and then you would have a removable cover that would snap on top of this. It's a fairly simple shape. It's just a basic rectangle, and if you design your circuit board correctly, you can use one of these, more standard type of products. These are a couple of different products that we make. This is an SMS shield, so these are standard off-the-shelf tooled up products. They come in a full catalog of sizes, so if you can design your circuit board to use a part like this, they're already made, they're on the shelf, they're the easiest type of product to use. This is a CBS shield, so if you look at the fence around the bottom section, you can see it looks like little fingers. So those are straight pieces of fence that we can form to different lengths and widths, and we have different options for heights. So it's kind of a modular design. So if you don't have something that's made for the ready-made off-the-shelf parts, we can design a shield like this that is kind of a modular type of design. The slot lock shield is a fully customizable type of shield. So when you can't make a standard product fit on your board, we can make this type of customizable shield that will fit to what you've already designed your board to be. And then this shield is an example of a fully customized product. Something like this is when EMI is an afterthought. And obviously something like this would be by far the most expensive type of shield. When we're designing an EMI shield, the first aspect that you look at is what type of material you're going to make the shield out of. So you have to ask yourself, how is the shield going to be used? Will it be in a corrosive environment, outside, in a vehicle maybe, or is it going to be indoors in a protected environment? So we have multiple options of material. So the alloy 770 is a copper nickel zinc alloy. It's what we use for corrosion resistant designs. It's non-magnetic and it doesn't require any plating. It's also what we use when we need to design a part that is welded from multiple pieces that have to be put together, so it welds very well. It also has excellent solderability. The next material is pre-tin plated steel. So pre-tin plated steel is our standard type of material. It's cheap, it's easy to manufacture, it has excellent solderability. The trade-off is it doesn't have good corrosion resistance. So if you were going to use this shield where it would be subjected to moisture, the metal has been plated from the mill, from the material manufacturer. So when you cut that metal to make a shape, you're exposing the bare edges of the steel, and they can be subject to corrosion. That being said, we make the vast majority of our products are made with this pre-tin plated steel, and it works for most applications. Another type of material is a phosphor bronze. This is a good material. It doesn't require any type of heat treating, but it does have moderate spring properties. So we've used this before. Say you had a shield that has a connector going through it, and you would put a type of a light spring finger to make contact on that connector and give you good grounding. That's something where phos bronze would come into play. The phos bronze does come pre-tin plated if you need it, but generally we see those are being post-plated after processing. Um, we do have the option to make shields out of pure copper. It is expensive, but copper does provide the highest conductivity, and technically it does give the best shielding, especially at higher frequencies. Um, you don't generally see customers needing to make a shield out of copper. It's not usually necessary. Generally, copper is reserved for battery contacts, connectors, things like that. And the last material on here is high mu 80. So when we were talking about the electromagnetic spectrum earlier, below what we saw for radio frequencies are magnetic frequencies, so in the hertz and kilohertz range. So earlier I had also mentioned about the EMI signal being absorbed into the material itself. So high mu 80 is a high permeability, so it essentially soaks up magnetic frequencies almost like a sponge. So that's a special type of material that we use for only low frequency applications. So in addition to trying to design a shield for good shielding purposes, you're also trying to make these parts easy to install. So there's a few aspects of the design that you have to look at when you're considering how you're going to install the parts on your circuit board. So the first we look at is what type of edge, whether you're going to have pins, solid straight edge, or castellations. So pins are sometimes used when you're doing wave solder, where they protrude through the circuit board and then it passes through a wave of molten solder, and then the pins are soldered underneath the board. Um, or pins are also good if you have a very complex shield. They can be used to hold it in place onto the circuit board trace. Solid edge is when you're doing SMT, where generally the shield is going to be automatically picked up and placed onto a circuit board. And then castellations are an interesting option where it breaks up that continuous solder trace and helps get good airflow and more even heating to get a better solder joint. Um, when you're looking at doing a shield, you have to decide whether you're going to do a one piece or a two piece. One piece is just a box that is directly soldered to the circuit board, and then it's not coming off. The other option is to do a two-piece frame and cover. So the frame is soldered down onto the circuit board, and then we design a removable cover. So this allows you to access components underneath while still getting great shielding effectiveness. When you're designing a shield for installation, one of the largest challenges we face is coplanarity. So these circuit board shields are generally installed in the same production line or manufacturing process that you would install a microchip. So it's a challenge to fit sheet metal parts into that same process. No matter what you do, those sheet metal parts are never going to be as precise as a mass-produced microchip. So we have to work with the customers to design for the coplanarity, the flatness. So you can see this shield. This is an example here of a shield where coplanarity is a challenge. So you're making this part out of welded pieces of sheet metal, and it's not going to always be very flat. So you can see this shield has multiple pins all the way around the frame, so that will help hold that shield in place on the circuit board. But it may not be very flat. So generally we see solder thicknesses between 3 to 4 thousandths, and that's not going to work with a very complex shield. So one thing we always try to get our customers to work with and use are fixtures. So these are a couple of examples of board level shield fixtures. So the shield would be placed onto the circuit board along the trace pattern, and then these fixtures are bolted down to hold them flat against the circuit board, as they run through the reflow process, and that helps to ensure that you get a good solder joint. These are also useful if you're soldering on both sides, so the shield would run through one cycle and then the board can be flipped over, and because of the fixture, the shield will stay in place as it's run through another round of reflow for components on the other side of the board. Throughout the presentation here, we've been talking a lot about traces and designing shields to fit on the circuit board trace. And proper trace design is one of the biggest key components for being successful with installing your circuit board shield. Over on the left here, you can see this is a circuit board trace, and then this frame is installed on the trace. When we talk about the trace, we want it to be a minimum of 3.5 times the material thickness. So this diagram here, this represents the straight edge of material of a circuit board shield, and the circuit and the solder joint, the trace pattern would be here, and we need that trace pattern to be an absolute minimum of 3.5 times what the material thickness is. So if you have a 10 thousandths thick metal, you need a trace thickness width of 3.5 times that, so 35 thousandths. And what that does is it ensures a good solder joint. The solder wicks up the side of the shield, and it gives you a good solid joint. Again, 3.5 times is the minimum. We always recommend more if you have the room on your layout, but that's definitely what we recommend. So the last aspect of the shield design is actually getting the finished product to you intact. The parts that we make are small and they're made out of thin gauge sheet metal, so they tend to be kind of delicate or fragile. So we have some standard packaging options, but depending on your application, we have a couple of special packaging options. So the first one on the left here is tape and reel. So you can see that these are shield frames that are installed in plastic tape in pockets, and these are designed to run through an SMT line. So any type of shield that's generally going high volume, we're going to put it in this type of packaging so that they work on the SMT line. If a shield is very complex or larger and it won't fit in tape and reel, we like to put them in a plastic tray. So you can see on the right that this is a thermoformed plastic tray. And what that does is it helps protect the part in shipping. Again, the shields are generally somewhat fragile or delicate, so we have to make sure that they make it to you intact. So this concludes our presentation today. I hope it was enjoyable and that you were able to pick up some good information on electromagnetic interference and how to design products for easier installation.